Hi everyone. Today I'll be talking about Model Predictive Control, or MPC. Model Predictive Control is extremely powerful and very robust, but it also comes at a high cost. Although MPC is very capable, until further development and research is done, it remains as a less than ideal control scheme for most applications. What I'll be covering in this video is what MPC is, and then I'll illustrate the power of MPC with some applications of MPC. Then I'll get into the major hurdle of MPC through an example of its complexity using a simplified first-order model. To start off, have you ever wondered how autopilot works? Or how electronic fuel injection works and is able to put just the right amount of fuel into an engine? Or even just how that thermostat in your house works and how it knows when to turn the AC on and off? These are all examples of systems that use control schemes, or control systems. Model Predictive Control, or MPC for short, is a cutting-edge control scheme for a control system. Just to be clear, MPC is model-based predictive control. We are not predicting the model of the system itself. We are only using the mathematical model of the system to predict what may happen in the future. One of the major benefits of MPC is it is extremely robust. It's able to handle all sorts of disturbances. We'll discuss that in a moment. As I said, it uses its current data set to predict the optimal control sequence, the sequence of control steps it will take to obtain some objectives such as a planned path or thermal regulation or power regulation or anything else. It will predict this optimal control sequence up to some time step in the future we will call the horizon. It will then take the first step in that predicted control sequence and then recalculate and repeat. Some things to note about MPC are first, the fact that unlike PID control, it requires a good mathematical model of the system. This is pretty significant as the model can be very difficult and even impossible to obtain. Second, MPC is able to handle system constraints. Many control schemes don't allow for you to handle things like amplifier saturation or maximum velocity or other system constraints, but MPC handles this nicely by using optimization programming. Third, the further away the prediction horizon is, the better the performance. To help illustrate this idea, let's look at something a little different: mountain biking. So let's say you're a mountain biker and you have some path with a few obstacles on it. They could be rocks or roots or whatever. If you only look at the ground directly in front of you, you only get a limited set of information. You may think that because you see an obstacle directly in front of you, your optimal path will get you safely around the rocks and roots. But because you only have that limited set of information, you can't plan for that rock that's further ahead, and you crash. But if instead you look further out, you have the information of what has already passed your viewpoint and is now right in front of your tire, as well as what is currently at your viewpoint. So you can effectively plan for all the obstacles within your path up to your viewpoint or horizon, and you make it safely through those obstacles. This is how MPC's prediction horizon works. So the further away the prediction horizon, the better the performance. But the caveat to this is that the further away the prediction horizon is, the more computationally expensive it gets, and it's an exponential increase. These algorithms require powerful and fast computing capability. So let's look at a few example applications of MPC. First, we have a drone. We all know that drones are very capable of stable flight, but let's say that one of the rotors fails. The blades break, or the motor cables are faulty, or whatever. What can previous control schemes do for this? Not much, unfortunately. But MPC is able to take the information that it has. The rotor load is gone, trajectory is changing quickly, and will be heading for the ground, and adapt its control on the fly. You can look up rotor failure testing and find videos of MPC helping a drone maintain some stability in flight. It's pretty amazing. Another example is drone racing. With a powerful enough computer on board, autonomous drone racing may become a thing one day. Control schemes such as MPC, used for optimal path planning and object avoidance, would allow a drone to effectively race through a course on its own. That would be pretty cool. Yet another example is Boston Dynamics Robot. This is Spot. He's a quadruped. If you haven't seen him before, look him up, and look up Atlas while you're at it. It's pretty cool. Boston Dynamics has combined optimal path planning and robust control schemes such as MPC to create a very stable robot system. This is incredible for a few reasons, one of which is that walking gaits and leg phasing are very difficult to manage and plan for. So in an attempt to illustrate how computationally expensive MPC can be for a system, I'm going to borrow the idea of our friend Spot here and model a single leg of a quadruped in the simplest way I possibly can. Bear with me here. It might get a little bit mathematically bumpy. To start, I simplified the leg to a basic swinging pendulum. Then, to further simplify, I ignored gravity. Gravity causes some nonlinear fun in the system that we'll just ignore here. It would be interesting to work with, though. This leaves us with the following first-order differential equation for the motion of the leg. And just to clarify, B is some estimated viscous friction, and E is an estimated efficiency constant for the motor swinging the leg. Note that this is really only one-dimensional, and in reality a robot such as Spot would need to consider multiple joints, rigidity of the leg sections, all 3 dimensions, and nonlinear gravity, as well as other nonlinearities. I just want to make it clear that this is a thoroughly simplified model. So now we get to the MPC for this super simple swinging leg. First, we note that we have some time-varying disturbances in our system. And what we're talking about here is ground force reactions that will make the leg bounce when it hits the ground. The steps to implementing MPC for this system would be, first, convert the first-order differential equation into state space form. This is pretty easy, especially as it's only a first-order system. Next, we need to formulate the algorithm as a convex quadratic programming optimization problem, which involves doing a lot of matrix algebra. This step isn't as easy, but still not bad. Just so you know, basically what a convex quadratic programming optimization problem does is allow us to minimize the costs of the system. And these are not computational costs here. We define the cost based on the intent of our system. For example, in autonomous drone racing, we might say that time is a cost, and so we want to minimize it. Also, we have the cost for not stopping in time before hitting a wall, which, by the way, that costs a lot for a drone flying 80 miles an hour. Once we've properly formulated the problem, we can begin to define the constraints of the system by finding these H and G values. This is a less easy step, as it involves doing some optimization, but all in all, it's not so bad. Basically, what we're doing is saying that we have boundaries on the time-varying disturbances, and we want to constrain the system states and system inputs based on what these disturbances may do for the system. So the H and G values are then added to the upper and lower boundaries of constraints for the system. Simple, right? Okay, hang in there. We're getting to the good stuff. Finally, we get to the main optimization problem we want to solve at each time step for this robotic leg. This is what it comes down to. And if you're interested, contact me and I'll let you know what it all means. Don't expect it to only take a few minutes, though. And if that makes too much sense for you, then also remember that what we're actually after is an optimal input sequence. We would then give the system the first set of the values from this input sequence, and then do this optimization problem again in the next step, which, by the way, is likely microseconds away from now, and then again in every time step. Remember that this is for a super simplified first-order one-dimensional model of one of 4 legs on a robot that still needs computational power to manage its vision algorithms and its path planning and everything else. Yikes. In conclusion, MPC is an extremely powerful control scheme for all kinds of applications, but it remains a little-used control scheme in the industry because of its computational expense. However, MPC is beginning to be used in systems that have enough time between time steps to compute optimizations, such as power and HVAC control. MPC algorithms are also very well suited for parallel programming, and may benefit from using a GPU or similar processor to divide and conquer the optimal control sequence prediction. This has been done on some applications, but it still needs further research. Thank you for watching. If you have any further questions, please feel free to contact me at james.jones@utah.edu. Thanks again.